everybody. But now we have to get to work again. And it's a great pleasure to present Thomas Kühn from the University of Leipzig to give the first talk today about pre-asymptotic estimates for approximation of multivariate periodic Sobolev functions.
Thank you. First of all, I would like to thank the organizers of the whole program and of the workshop in particular for inviting me and giving me the opportunity to present the talk here. To those who have heard similar talks of mine, I apologize, but as Hendrik said, repetition is the mother of wisdom. Well, I don't pretend I have the wisdom, but it's an excuse. Okay, so I will talk. I mean, the subject of the talk is approximation of functions on the d-dimensional torus. So we will always be concerned with a periodic case. So the functions I will consider are from the isotropic Sobolev spaces and from Sobolev spaces of dominating mixed smoothness, the very classical spaces. And the quality of approximation is expressed via approximation numbers, which appeared already in several talks here. And the error is measured in the L2 norm, and at the end, maybe if I have time, I will make a few remarks on approximation in the L infinity norm. So my special emphasis is on optimal asymptotic constants and on sharp pre-asymptotic estimates. I will explain in quite a bit of detail the philosophy which is behind these pre-asymptotic estimates, why they are useful, or why do we need such things. And well, the subject is related to functional analysis. That's the area where I come from, approximation theory, numerical analysis, and also to information-based complexity. Okay, approximation numbers, I can go fast through this slide. They appeared in previous talks already, and they are well known. For bounded linear operators, t from x to y, x and y are Banach spaces, or maybe also quasi-Banach spaces, which will not be the case here in this talk. The approximation numbers are defined. The nth approximation number is the best approximation of the given operator t by an operator of rank less than n. So if these approximation numbers tend to 0, then t is compact, and in strange spaces, let's say, the converse fails. This is N-Flo's counterexample. We will be mostly concerned with the Hilbert space setting, and there we have an equivalence. Because for compact operators in Hilbert spaces, between two Hilbert spaces, the approximation numbers coincide with the singular numbers, and the singular numbers Sn of t of the operator are defined as the square root of the eigenvalues of t star t in decreasing order. So t star t is a positive self-adjoint operator. The eigenvalues are positive reals, so we can order them. Okay. So the relation to numerical analysis and or information-based complexity is as follows. If we consider an operator of finite rank a from x to y, then we can always write this operator as a sum of n summands, each summand of the form a linear functional applied to x multiplied with a vector from the target space. So that means we have n linear functionals and n vectors which determine this operator. From a numerical point of view, we can view this as an algorithm. So what is the input? I mean, we want to approximate a given operator t at x. So the information we have are these n linear functionals of x, and with this information we build this operator which should serve as an approximation of tx. So this is a linear algorithm, and it is using arbitrary linear information. Arbitrary means that we have arbitrary linear functionals. In other talks, it was just function evaluations. This is standard information. Okay, so the error of the operator of the algorithm evaluated x is norm t x minus norm tx minus ax, and the worst case error is if you take the supremum over the unit ball of the first space. So, but this is the operator norm of t minus a. And the nth minimal worst case error of the problem, t, is so the best algorithm that we can have here if we restrict to operators of rank less than n. So this infimum of the error of the algorithm is on one hand the worst case error in the sense of IPC or numeric analysis, and on the other hand it's the n plus first approximation number. So this is a relation. I will not come back to this too often. So now to Sobolev embeddings. So as I said, I will deal with very classical spaces. So what is well known, and this can be found for instance in Volodya's books or in many other papers, for isotropic Sobolev spaces, not only on the d-dimensional torus but on more general domains, but I will consider this case only, the embedding from the Sobolev space with fractional smoothness S into L2, the approximation numbers behave asymptotically like n to the minus S over d. And this appeared already in Holger's talk. This is a very classical result. But we have matching estimates, but with constants. A lower constant, which depends on the parameters of the space, namely smoothness S and dimension d, and an upper constant here. So let's say 20 years ago, no one cared about the constant. They said there is a constant. And this meaning that, well, the smoothness is fixed, the dimension is fixed, and then we have a constant. But nowadays we are interested in the dependence of these constants on the dimension and on the smoothness. So another classical result is for Sobolev spaces of dominating mixed smoothness. I denote them by H as mix. So the mixed smoothness is S. And if you embed this into L2, the approximation numbers behave now like log n to the d minus 1 over n, and all this to the power S. So we have, again, the same bound here, upper and lower bound, but with unknown constants. There's much less known on this. But in high dimensions, for numerical problems, it is important to know these constants, or to have some information on these constants. And this is also important for tractability problems in information-based complexity. So, some comments first. I mean, here in this context, it is clear that these constants, these little CSD, lowercase CSD and capital CSD, they heavily depend on the norms that we have chosen in the space. And usually on the Sobolev spaces there are many, many different equivalent norms. So, but let's have a look at the pre-asymptotic range. That means where n is small, let's say n less than 2 to the d. This 2 to the d is not important. It could be 5 to the d or 10 to the d, but something which is of this. But in this range, the asymptotic rates are absolutely useless. Look at n to the minus S over d. I mean, it's clear if d is increasing, the rate is deteriorating more and more. But in this range, plug in n is 2 to the d, then this is a constant. Then it is 2 to the minus S. So this rate is, in that range, almost a constant. And in the dominating mix case, it's even worse. If you look at this rate and check the properties of the function behind that, it shows that this is increasing up to n of e, if n is e to the d minus 1. And the value of this function is then something like d minus 1 over e, all this to the d minus 1. So it's super exponential in d. That means in this range, this asymptotic rate is completely nonsense, because we are comparing a decreasing sequence of approximation numbers with an increasing function. So this makes no sense. On the other hand, for numerical issues, 2 to the d might be already far too large. Hendrik mentioned in his talk problems where the dimension is several hundreds. So then 2 to 300 or whatsoever, this is too much for the computers to deal with. So that means what we need are information on the constants, in particular the dependence on d, and this might help in our in the practice and pre-asymptotic estimates. So, as I said, these problems are very sensible with respect to change of the norm, so I have to fix the norms. So on the Sobolev space, the classical isotropic Sobolev space of integer smoothness m, there are two more or less classical norms. The first one is working with all partial derivatives up to order m. So you take all these partial derivatives, L2 norm of this, and sum this up in the L2 sense. So this is the original norm, let's say. And then a modification of this norm is you take only the highest derivatives in each coordinate direction. So you take the L2 norm of the function and then only the highest derivatives in each direction. These are equivalent norms. So this was our model to introduce somehow natural norms on the spaces we are using. So we can easily rewrite both of these norms in terms of the Fourier coefficients. And so the torus here for me is an interval 0 to pi with the endpoints identified and normalized Lebesgue measure. So these are the Fourier coefficients. Everybody knows that. And for this classical original norm, we get the following. The norm is equivalent, but here it's important to notice that the equivalence constant depends only on smoothness but not on dimension. So this is already an advantage. And then it is this expression here. This is the L2 sum of the Fourier coefficients with a certain weight. And for the second norm, with only the highest derivatives, we get a similar expression, even equality here. Again, a weighted L2 sum of Fourier coefficients, but now the weight is this here. So have a look at the weight. So here the weight is basically the 2 norm of the frequency vector to the power m. And here it's basically the 2m norm of the frequency vector. And it's clear we are in a d-dimensional space that they are equivalent, but the equivalence constants depend heavily on d. Okay, so these models lead to the definition of the spaces we want to consider. So we consider isotropic spaces of fractional smoothness. So d is a dimension, s is smoothness, and now we have an additional parameter p between 0 and infinity. One could also include p equal infinity. I exclude it here because then we would have cursive dimension, and this and we have no pre-asymptotic estimate. So therefore I exclude p equal infinity. So this space, the superscript p only indicates which of these norms we are using. And the norm with parameter p is again a weighted L2 sum of Fourier coefficients. Now the weight is basically the p norm of the frequency vector to the power s. So clearly, if you fix the smoothness and of course the dimension, then all these norms are equivalent, but with equivalence constant depending on d. As vector spaces, all these spaces coincide. It's just hs. Well, to remind you, so for the classical norm we have the equivalence with the new norm where the parameter is 2 and the constants are independent on d, which is important. And for the second norm we have even equality where the second parameter is 2m. So this is a motivation, and this tells us our norms are somehow natural. I mean, it's not clear what is a natural norm. So and for Sobolev spaces of dominating mixed smoothness, we proceed in the same way. S is the smoothness. Again, we introduce an extra parameter p and denote the Sobolev space of fractional order S, the mixed space, equipped with this norm p by the symbol HSP mix. And here, again, it is the norm is a weighted L2 sum of Fourier coefficients, and the weights are now these products. And for everybody who worked with a hyperbolic cross, it's clear here somehow hyperbolic crosses come into play. So, and for integer smoothness, again, all these spaces for any p and fixed smoothness m, they coincide with the very classical Sobolev space of dominating mixed smoothness, where we have all derivatives in L2 for all multi-indices with each coordinate less than or equal to m. Okay. So there's a general structure behind. So we have certain weights, wk. We define a norm as weighted L2 sum of the Fourier coefficients with these given weights. And let me denote for the moment the corresponding space by hw with a maybe w from the weight. So in all the previous examples and of spaces and norms, our weights are as follows. They are somehow normalized that at 0 the weight is 1 and all our weights are bigger, and if the frequency vector tends to infinity, then the weights tend to infinity. And this ensures that we have always an norm 1 embedding from this space into L2, and this embedding is compact. So, and so this allows to reduces everything to sequence spaces. So here is our embedding from HW to L2, and now you might think of any of the spaces of isotropic or mixed spaces I mentioned before. So you have the following diagram. We take an operator A which maps a function onto the Fourier coefficients and the weight, and then clearly the norm in L2 of this guy here is exactly the norm of the function in the Sobolev space. So this is an isometry, even a unitary operator. And here I have a similar operator from L2 ZD to L2 over the torus. This is here. So you take a vector in L2 set to the D, take this as the frequencies of a function, and then it's clear that the L2 norm of the function is exactly the L2 norm of the sequence. So again we get a isometry or even a unitary operator. And in order to make this diagram commute, we have here an operator, and we have to divide each coordinate by the weight. So that's all. So this is a diagonal operator, and then from this diagram one can easily see, because we also have a corresponding diagram with A inverse coming from the space here and B inverse from L2 of the torus to L2 of ZD, that approximation numbers of this identity embedding is the same as approximation number of this diagonal operator, and the approximation numbers of this are the singular numbers. Singular numbers are the eigenvalues. The eigenvalues are 1 over wk. So the only thing you have to do is we must rearrange. So let's denote the non-increasing rearrangement of this diagonal entries of the diagonal operator 1 over the weight by sigma n. And now n run through the natural numbers. So in order to find this rearrangement, we consider these cardinalities of all of the set of all k and zd such that the weight is less than a certain threshold r. So if this r happens to be one of the values of the weight, then the approximation number with this index nrd is exactly 1 over r. So if you have this for sufficiently many r's tending to infinity, we have in principle full information on this an. But only in exceptional cases, exact formula, an exact formula for this cardinality is available. In all other cases, we are forced to look for good estimates, and this is done by combinatorial arguments and volume estimates, as usual. Okay, here are some results. So that's a point where I should mention my co-authors. Most of the results I'm presenting now are joint work with Winfried Sigel and Tino Ulrich, some with Fernando Cobos, and at the end I will present some very new results. So if we consider the isotropic spaces HSP and embed into L2, then the rate was n to the minus SD. So we multiply by the rate, and it turns out that here even a limit exists, and the limit can be expressed by volume of the p ball in the dimension d. So that's the usual LP norm, whatever p is. And this volume to the s over d behaves like, as d goes to infinity, roughly like d to the minus s over p. So that means this asymptotic constant I mean, this could be considered as follows. If you remember the first slides where you have these upper and lower constants, if you go to larger and larger n, then you might shrink the constant to better lower and better upper constant. And in the limit, they then have the same value here. So for the classical norm, this is d to the minus s over 2, and for the modified norm, d to the minus 1/2. And here you see already a certain influence of the different norms, which is in this parameter p. So, and we get, of course, the correct order n to the minus s over d of the approximation numbers and the exact decay rate of the constants. And this is a polynomial decay which might help in error estimates. So now the pre-asymptotic case is as follows. In a paper with Winfried and Tino, we got for the norm with parameter p equal to 1 a two-sided estimate of the embedding of HS and L2 in this pre-asymptotic range, and the bound now is logarithmic in n. It's log n to the minus s. But here you see this blue factor log 2 of 2 to d to the 1. This is a gap, essential gap between upper and lower bounds. It's not quite matching. And moreover, the proof, which was relying on an exact combinatorial formula, worked only for this case. So next, in a paper with Tino Ulrich and Sebastian Meyer, we got the correct order, and in this case. Now all norm parameters p are allowed, and we got this through an interesting connection of these approximation numbers to the entropy numbers of the embedding of the identity of the embedding from LPD into L infinity D. So we got the correct order here, and it turned out that in the nominator we don't have the 1 as in the lower estimate before, we don't have log D as in the upper estimate before, but it's D over log N. This is the correct order, and to the power S over P. But this holds up to equivalence constants depending on S and P, and we did not really figure out the exact constants. So, but what is interesting to see, the strong influence of the norm parameter. This appears here even in the exponent of the logarithm. So the norm and the influence of the dimension is fairly mild. So we did not provide explicit constant. Now this is a new result. Maybe it's not so important to look at all these constants. So, but the point is here, for the same embedding from the isotropic space HSP into L2 in this pre-asymptotic range, roughly, I got explicit constants. So here you see d over log n and d over log n, and with 3, 2, blah blah blah, whatever. It's explicit constants. I formulated this here only for norm parameters p bigger than 1, but I have estimates for p between 0 and 1, 2. Okay, so now to the dominating mixed case. Of course, the strategy of proof is the same as for isotropic spaces. I mean, it's this general strategy. If you have a space where the norm is given by L2 sum, weighted L2 sum of Fourier coefficients. This is what I denoted HW. So, however, the combinatorics here is now a bit more involved. And as I said, if we study these cardinalities I mentioned before, then we are left with estimates for the hyperbolic cross. I will not give this in detail. So, and here, together with Winfried and Tino, in another paper, we got the optimal asymptotic constants for this embedding of HSP mix into L2. P, again, remember, is only a parameter. And so I divide this AN by the asymptotic rate, and in the limit, we get this value 2 to the d over d minus 1 factorial to the power s. What is more surprising for us that the limit is independent of the norm parameter p. It's always the same. And if you have a look at this here, this is something like 2e over d to the power d. So this is super exponentially decaying in d, and this is helpful in estimates, of course. So in the pre-asymptotic range, we got the following. So this is again in cooperation with Winfried and Tino. So we restricted to the case of mixed spaces where the norm parameter is 1, which is a little bit easier to handle. But we had also other results. I only mentioned this here. So for n in the range from 8 means because otherwise we would have a trivial estimate, to roughly 2 d to 4 to the d, roughly, we get an upper estimate of this type. The nth approximation number is less than or equal to e squared over n to this power, s divided by 2 plus log 2d. Okay, so as I said, this bound is non-trivial from 8 on, because then the factor is less than 1. So, and we have similar lower estimates which are more complicated looking, but at least they show that this asymptotic rate n to the minus s, if we ignore the log terms for a moment, can be seen only after waiting exponentially long. That means in this range the asymptotic rate cannot be seen yet. So here we still have a polynomial decay. I mean, roughly the polynomial rate is n to the minus s for the asymptotic rate. And here, and plus these logarithms. But here, this s is deteriorated a little bit, because if the dimension increases, the rate is getting, the exponent is getting worse and worse, but slowly getting worse. Okay. So, and I have another small improvement of this for this same embedding. We have an estimate similar type as before. Now the constant is not e squared, but 16 over 3. So 16 over 3n, and to the power s 1 plus log 2d. So this is better in a few respects. I mean, first of all, the range of n is larger. The factor 16 over 3 is smaller than e squared. But what is most important, the exponent, it is now 1 plus s divided by 1 plus log d. This is better than s divided by 2 plus log d. And from a intuitive point, this fits very well to the one-dimensional situation. In dimension 1, well, not really. In dimension 1, we get s over 2. So this is, and in dimension 1, the correct rate is s. So it's very close to the. Okay. So finally, I have a few minutes, yeah. Sure. finally, I will give a few remarks on L-infinity approximation. So, of course, we can also consider embeddings of these spaces are introduced into L-infinity. What is well known is again the asymptotic rate of approximation numbers. And recently, fairly recently, a few years ago, with Fernando Cobos and Winfried Zickel, we got a relation between approximation numbers of embeddings into L-infinity to, I mean, in this case, if the spaces embed in L-infinity, they also embed in L2. So, and we got an expression for the approximation numbers for L2 approximation via L2 approximation. And I decided not to write down the formula because I thought I will run out of time. So you can check it in the paper. So, but as a consequence, we get for the same norm parameter and also all S. I forgot to write that. No, I didn't forget. So in the isotropic case, if we use L2 approximation, the rate is n to the minus s over d, and we have an embedding of hs into L-infinity if and only if s is bigger than d over 2. So that means if s is bigger than d over 2, still something is left. We have here the approximation numbers divided by the asymptotic rate, which is slightly worse by 1/2 as for L2 approximation, and times a constant. And the constant is the constant from the L2 approximation with an additional factor. So this is a correction factor, but again, an optimal constant exists. And similarly for the mixed spaces, then we have an embedding if and only if s is bigger than 1/2. So, and here again, consider the limit of the approximation numbers of this mixed space into L-infinity divided by the asymptotic order, and the asymptotic order is the same as for L2, except that we have an extra 1/2 here. And again, it turned out a limit exists. The limit is equal to the limit in L2 times a correction factor. But you see, if s goes to 1/2, then 2s minus 1 goes to 0, so this correction factor blows up. And I will finish with an open problem. We have no idea about the pre-asymptotic behavior. Thank you for your attention.
Thank you very much. Are there questions? Yes, for me.
It's more like a remark that I think these results about pre-asymptotic behavior are very important and interesting. But also we should keep in mind that these results are very sensitive to minor changes of the class. For instance, if you take this mixed smoothness class, in that weight it was like 1 plus absolute value k to some exponent, whatever. So if you replace this by, for instance, maximum between 1 and absolute value k,
absolute change. Then you get the curse of dimension, no pre-asymptotics, nothing.
This should be taken into account.
This is.
Any further questions? Yes.
In your definition of Sobolev space, you always use the Fourier coefficients weighted. Have you tried to see what happens if you use wavelet coefficients?
Well, then,
Fourier coefficients?
Of course, in principle, you can also use wavelet coefficients, but then you have to have very good control on the equivalence constants between the. Of course, you can use wavelet coefficients and define the space via wavelet coefficient. Now, if you define the space just, it's a set of all L2 functions with these and that wavelet coefficients, then this can be done also. Yeah.
One final short question.
No, go ahead.
So, okay.
Short question.
Yeah.
Well, in L2, the approximation numbers are equal to singular numbers, and then L infinity. Can you say a few words? How can you get such sharp asymptotics?
Yeah. I can say a few words. So, we let's say from HS. to L infinity. So then, of course, we are out of the Hilbert space setting, but we can embed into L2. And this here, this embedding, from the point of view of function analysis, this is absolutely two-summing. So, and then not the approximation numbers, but the Weil numbers. I don't go into detail of this embedding here. The Weil numbers are less than n to the minus 1/2 times the norm of the embedding, which is 1. So, and we have a Weil numbers here also, approximation numbers and Weil numbers and Gelfand numbers and Kolmogorov numbers in the Hilbert space setting are all the same. And then you have at least from this diagram you get a lower estimate. Or we can discuss later. Or I can show you the paper. So.
All right. Well, thank you very much again.